If a matrix is invertible, there are non-zero pivots along the diagonal entries. Getting you down to the identity matrix means trying to put you into a triangular form. And so what we're going to do is apply a bunch of row operations to the matrix A to turn it into some triangular matrix U. In order to change a matrix into a triangular form, you only need row swaps and replacements. You don't need to do scalings. You might say, well, what do you mean you don't need scalings? It's just more work and a lot more thought that has to go into which replacements you'll do. But really, these are the only two you need. So that means that the determinant of any one of these elementary matrices that you're going to apply is either going to be a +1 or a -1. It just depends on if it's a replacement or if a swap. So for any n by n matrix, if we do a bunch of these row operations, either replacements or scalings, to take it to this triangular form, we have a wonderful result about a triangular matrix and its determinant. All we need to do is look at the diagonal values. This is going to be some elementary matrix multiplied with all these other ones onto A. Now, we said that if you ever have an elementary matrix times a matrix, these determinants get to split. So it's the determinant of all the rest of them times A. Now, if I just repeat this, I can generalize this all the way down. I'll have all of these individual determinants multiplied together times the determinant of the matrix A. Now, because these are all swaps or replacements, I will either get a +1 or a -1. This quantity is just going to be a -1 to the power of r times the determinant of A. And r is going to be the number of row swaps that I did. That's the only thing that could ever change the sign. So what this is telling me is that the determinant of any matrix A is going to be -1 to the power of r times the determinant of U. So all I need to do is to take a matrix A, put it into a triangular form, keep track of the row swaps, and I will be able to say something about the determinant of A. So if I take a 4x4 matrix, this would be painful to do by cofactors because there's no zero row or zero column that's obvious for me to exploit. So instead, what I'm going to do is try to row reduce this to a triangular form. So I'll take the top row, and all I need to do are replacements. So there's going to be no change to the determinant. I'm going to take -2 bunches of 1, add it to 3 to make the new 3. I'm going to take 3 bunches of 1, add it to 4 to make the new 4. 0, 1, 2, -5, -1, -2, +5, 0, 2, 4, -10. So if I call this matrix U1, the determinant of U1 will be exactly the same as the determinant of A. There'll be no change there. Now, to get it to triangular form, I have to do another row replacement. I'm going to add 2 to 3 to make the new 3, and I'm going to add -2 bunches of 2 to 4 to make the new 4. I'm going to call it U2. The determinant of the matrix that I get is going to have no change. 0, 1, 2, -5. I can see that these rows are identical, so I'm going to get a row of zeros. And in fact, the bottom 2 rows are identical. The determinant U2 is equal to the determinant of U1, which is determinant of A. Because this is triangular, I'll get it 1, 1, 0, 0. The determinant of U2 is 1 times 1 times 0 times 0, which is 0. That tells me some really important facts here. The determinant of A is just the determinant of this U2, which is 0. That's the first thing I should note. The second thing I should note is that A cannot be reduced to the identity because there are zeros for pivots. That tells me A is not invertible. And so the connection that I want you to make is really what we set out to kind of come up with here at the beginning. A is going to be invertible if and only if the determinant of A is non-zero. The determinant is a number that tells us whether or not the matrix will be invertible. If the determinant is 0, matrix is not invertible. If the determinant is non-zero, the matrix will be invertible. Now here's another useful result. if I want to talk about the product of two matrices, I would love to know what that's going to give me. When you take a matrix and it's invertible, you're going to be able to take the identity and get it as a result of applying a whole bunch of elementary matrices to A. This thing here would be A inverse. So if the matrix is invertible, that would exist. Now at the same time, I could reorganize this and say, oh, it would be the inverse of all of these acting on the identity. I could apply all of these things in reverse order and use their inverses. Something we talked about in class last time was that the inverse of an elementary matrix is the same type as the original. So if you have a row swap, its inverse is another row swap. If you have a row replacement, its inverse is another row replacement. All the results about the determinant of those inverses still hold. So if I wanted to calculate the determinant of A times B, that would be like saying take the determinant of all of these elementary matrices applied there. This is just some other elementary matrix. So I'll call it E alpha, E gamma down to B. By our previous results, we know that you could just turn this into a determinant of that times the determinant of the remaining product. And if I just repeat this, I'm going to end up with all of those individual determinants multiplied together times the determinant of B. And if I do one more combination of this, run this in reverse, this is just going to end up combining all of these back together. E alpha all the way down to E gamma, determinant of B. But that thing is A. So I end up just getting the determinant of A times the determinant of B. So here's a nice handy little result. The determinant of a product is product of determinants. So if I give you a matrix 1, 0, 1, 1, 1, 2, 1, 2, 1, the determinant here is going to end up giving you a -2. So if I asked you for the determinant of B squared, it would be the determinant of B times B. That would be the product of the individual determinants. So it would be the determinant to the power 2, which would end up giving me a 4. Similarly, if I was asked to calculate the determinant of b to the 5, I would play this game, b to the 4, and I would just keep repeating the product that I got, the determinant of b to the 4, and I would repeat the process here. I would eventually get up to the determinant of b to the power of 5, which is -32. What would I get if I was asked to calculate the determinant of 2b? 2b means scale each row of b. I have 3 rows, each of them scaled by 2. And so when I do a row scaling, it's just going to be that scaling factor multiplied by the determinant. So I'll end up getting an 8 times a -2, which is -16. So we've got a ton of results. They're all just different ways of calculating the determinant. And we are going to exploit that a lot when we go on to the next chapter of the course and we talk about something called eigenvectors.